Hello everyone, I'm Yige Liu. I'm from Philip Yuan's research team at the College of Architecture and Urban Planning in Tongji University. Today, it's my great pleasure to introduce you our design research for knitted fabric reinforced composites based on advanced knitting. We will take a knitted composites tower as an example to illustrate a computational workflow that gives full play to the material's potential. First, I'd like to introduce a little bit about the material. Knitted fabric reinforced composites is a special type of fiber composites, and the reinforcing fibers are knitted into fabric preforms and cured with polymers. The reasons for our research on this material is due to the environmental concerns for building materials. The 2018 Yuan report shows that the building construction and operation account for nearly 40% of energy-related carbon dioxide emissions. And among that, building materials account for 28% of annual building-related emissions. The carbon emission from building materials mainly come from conventional building materials, such as concrete, steel, and glass. Therefore, our team is looking for a more sustainable material for architecture industry. And the knitted fabric reinforced composites attract our attention due to several features. First, it's lightweight and high performance. Its density is 1/7 to 1/8 of that of stainless steel. Reinforcement and material mass can be added or reduced where is needed. It also allows flexible definitions of local fiber compositions, fiber directions with an accuracy in millimeters. Second, it is material saving and labor saving. Advanced knitting is able to directly produce net shape and detailed preforms, eliminating the material wastage and laborious work caused by cutting, sewing, drilling process. Third, this material is also suitable for low-cost mass customization, which is important for architectural production. It has a low production cost and high production efficiency for products with intricate shapes and complex details. To further explore the material potential, we challenged ourselves to design and build a self-support tower with this material. Regarding the design challenges for the material system at macro and micro scales, we propose a computational workflow, and this workflow covers 3 aspects. The structural form generation deals with the design of structure form. The structural arrangement deals with the design of structural elements, and the microscopic configuration deals with the design of stitches and yarns. In structural form generation, the major challenge is that how to design a structural form to enable a material that is only 2 to 3 millimeters thick to support a structure that is about 7 meters tall. The thickness of the material is limited by available knitting machines. Given this condition, we finally achieved the structural effective thickness and stability through the introduction of creases. The final structure surface of this tower is composed of 36 vertical creases. The pattern, depth, and the quantity of the creases are determined through comparative study using finite element analysis. The study result indicates that deeper creases at the bottom of the tower can increase local stability, and shallow creases at the top of the tower can increase global stability. Therefore, the final form of the tower has a flat upper part and a wavy lower part to maximize both the local and global stability. In structural arrangement, the major challenge is how to design structural elements to optimize force distribution and to make them easy for fabrication and assembly. The structural elements in knitted composites tower include 35 pieces of customized knitted preforms, steel plates for shape control, screws and nails for connection, fiber ropes for reinforcement, and a wooden base. The knitted preforms are arranged vertically along creases and the force flow. Each preform can be as long as 8 meters, which fully take the advantage of automatic knitting process and minimizes the connections. The 3D shapes of each preform is controlled by inserting steel plates into the sleeves along the edges of the preform. Neighboring preforms are connected through preserved screw joints on preforms and steel plates. We also introduce holes and reinforcements to optimize force distribution. We use the combination method of topological optimization and finite element analysis to inform the distribution of holes and reinforcement. In microscopic configuration, the major challenge is how to inform the distribution of stitches and yarns. A stitch is a microscopic structural element as well as a fabrication unit of knitted fabric reinforced composites. We developed a program that can directly convert 3D geometries as well as structural design information into a model of stitches and yarns and generate knitting codes. The program first unfolds the surface of a knitted preform, then translates structural patterns and assembly details into dots and curves. Then areas with different stitch structures are labeled out with different colors, and stitches are abstracted into a grid of rectangles. This grid of rectangles is then optimized to make sure that the layout of stitches follows a continuous knitting path. After the optimization, machine actions are defined through different units with different colors. At last, the 2D graph is converted into a pixel-based picture through non-uniform scale. This picture can then be directly imported to the knitting software, such as M1 Plus, and directly produces knitting codes for the knitting machine. Due to the thoughtful design, the fabrication and assembly process went on smoothly and was completed in 2 weeks. The fabrication of knit preforms cost around 137 hours. The only framework for the knit composites tower was reusable scaffolds and a top wood panel for hanging the preforms. The steel plates for shape control was fully integrated into the material system and became a reinforcing part of the structure. As a result, we finally achieved a 7.2 meter, 260 kilogram self-support, lightweight, stable tower. Compared with structures using conventional building materials such as concrete or steels, the knitted composites tower uses a minimum mass of material to achieve the effective structure and produces little material waste during the whole process. This experiment demonstrates design potential and sustainability advantages of the knitted fabric reinforced composites for architecture applications. The major limitation of this research mainly lies in the problem of wrinkles. Those wrinkles can be eliminated by improving the workflow as well as the positioning system. In future, we will add those improvements into the workflow and seek to establish architectural products with knitted fabric reinforced composites. That's all about our design research for knitted fabric reinforced composites. And thank you for listening.